Morning, everyone. So yesterday we started into our electrochemistry chapter. We introduced our main type equation as referred to as a redox reaction. Those are two halves of a whole equation. One side of the equation, oxidation, is involving a species that loses electrons. Those electrons are actually passed over to the chemical that gets reduced and actually gaining electrons. We had a nice memory aid here that we can say Leo the lion says grrr. Just spell it G-E-R there, and therefore you can always remember a loss of electrons is oxidation, while a gain of electrons, E minus is electrons, is reduction. We had talked about previously, well, if I get reduced, I usually think of losing stuff. Why is a reduction a gain? It just turns out the things that I'm actually gaining happen to be negative. It's actually my charge that's actually coming downwards. So for the first styles of questions that you're going to see is just identifying which species got oxidized, which species got reduced, who are your agents, oxidizing agent, reducing agent. You can also ask questions, well, is it a redox reaction? Let me just give you an example of some of these problems here. So just as a warm-up. Number one, I want you to identify if this reaction is redox, right? Where we learn redox, it actually involves a transfer of electrons, right? I'll give you this one, silver plus reacts with Cr2O7 minus 2, and water, one-way arrow ends up giving you silver chromate, He2CrO4, and an H plus. In today's lesson, later on, we're going to start talking about balancing. We're going to be adding waters and H pluses to make sure the atoms are all accounted for. More on that later. At this point here, we're just trying to identify, is this redox? Okay. The trick about this question here is it's hard because I do see charges changing, right? It's like, okay, silver is going from a plus, and then now it's in compound. Earlier, the hydrogen was sort of in a compound. It seems like it's neutral, then it's charged. Is an electron actually transferred? Remember last day we had introduced this whole notion of oxidation number and oxidation state. That was not a real charge, but they were numbers that if the number went up, oxidized. If the number went down, reduced. So what you're going to do to try to answer this problem here is you just want to go through and you want to just tell me what are the oxidation numbers of absolutely everything. So those, just sort of following through the list of rules here, we have some simple ions. Silver in a +1 state is just +1. Hydrogen, also simple ion, is +1. Now, in most compounds, hydrogen is usually +1, oxygen is usually -2. Let's try water. Hydrogen is +1, oxygen is -2. We also have that rule that when you add up all the oxidation numbers, the sum of the oxidation numbers in the compound, they have to add up to the overall charge. Well, water is a neutral overall. Well, 2 times +1, every oxidation number is defined per atom. That gives you +2 minus 2. Perfect, that cancels out. Probably the harder compounds here are these dichromate and silver chromate. Let's go through and get some practice here. Oxygen here is -2. Each atom is -2. There's 7 of them. That amounts to -14. 2 chromiums minus these 14 have to give you a -2. You should be able to tell me that the 2 chromiums have to be a +12, and therefore each chromium is like a +6 charge. Let's try the other side here, silver chromate. Silver again is +1 here as an alkali metal. It's not quite an alkali metal, but it does +1. 2 times +1 here is +2. -2 is for oxygen. There's 4 of them. That gives you a -8. 2 minus the 8 gives you -6, and therefore the chromium is also a +6. So how do we tell this one here is a redox reaction or not? We want to see whether there are any changes. If you have a situation where your oxidation number increases, your change in oxidation number is actually positive, that actually implies an oxidation. If your oxidation number actually drops, this one here implies there's a reduction. As you just compare the charges here, you end up realizing, oh, we have silver +1, silver +1. Chromium is like a +6, it's still a +6. Oxygen is -2, oxygen is -2, hydrogen is +1, hydrogen is +1. You notice there's actually no change, so we can actually conclude this one here is actually not a redox reaction. Even though at first it sort of looked like the charges were changing, I go from having a charge and not having a charge later on. Once you sort of work out those oxidation numbers, you realize no electrons have actually been passed. Okay, So I'm going to give you another example here, also trying to identify whether it's redox or not. This one here should be a redox reaction, so I'm going to ask you to further state which species loses electrons, which species gains electrons, and state your agents. So state the oxidizing agent, state the reducing agents. Okay. So let's have a look at a expression here. So I'm going to do this equation. We have AS4 becoming NaOCl. This one becomes 4ASO4 minus and NaCl. Right. Again, we'll talk about the balancing more in today's lesson here. Usually what I like doing here is I like translating the statement for myself. It may be hard to actually identify who's lost electrons. Well, a loss of electrons is actually an oxidation. So I could have reframed that and I could have said, can you identify for me who's oxidized? Who is the guy that gains electrons? Well, gaining electrons is actually a reduction process. I could have restated that, well, who gains electrons as who got reduced. Remember, when we're started classifying these chemicals here, we're always referring just to the reactant side. So we're just looking at these guys here. A hint for you, how do you identify something as a redox reaction? If something goes from an elemental state on one side and a non-elemental state on the other side, it probably is a redox reaction. What I mean by that here, we have arsenic, although the arsenic here is strangely is AS4. It's almost like a diatomic, but there's actually 4 atoms together. I go from an elemental state here. This is sort of like having all 4 arsenics as a 0 state, and later arsenic is actually in compound. When I check the oxidation numbers, -2 times 4 is -8. Arsenic is actually in the +7 state. Going from the elemental to a compound state involved a change. I went from 0 to +7. It actually gained by 7. I know the gain in oxidation number is going to be oxidation. Well, I thought gain was reduction. Well, in this case here, I would actually have to have lost electrons to actually have my charge go up. So that's why it's really easy to get sort of mixed up in terms of your terminology here. The best way around it here is just translate it for yourself, right? So if the oxidation number goes up, memorize it's an oxidation number. Oh, Leo the lines is GUR, oxidation is loss of electrons. So the chemical, the reactant that was involved, this is the chemical that lost electrons. This chemical actually passed electrons over to the sodium OCl compound. How about for the other compound? Let's check to make sure that there's a reduction. We can't have both chemicals willing to toss electrons, both chemicals sitting around waiting for electrons. Just like in the acid-base chapter, we need to have one guy donating, one guy accepting. So let's take a look at this sodium OCl. The sodium here is a +1. The oxygen is usually given -2. What charge does chlorine have to make sure that overall it's a near 0 charge? So far I have a 1 minus a 2 gives you a -1. Chlorine is sort of like having a +1 charge. That's not a real charge. That is an oxidation number. When I take a look at the sodium chloride compound, more standard, sodium is an alkali, so +1. Chlorine is a -1. You'll notice for all these oxidation numbers, I'm putting sign first and the number. That actually mark you wrong if you put 1 minus or 1 plus. We're going to track the change then. It's actually the chlorine part here that actually goes from +1 over to -1. This one here actually drops by 2. Whenever oxidation number goes down, I know right away it's reduction. Well, reduction actually involves gain of electrons. The chemical that was involved with this, it's the Cl part of the NaOCl. I still quote the whole compound. This compound is the chemical that got reduced. This is the chemical that ended up picking up the electrons. Lastly, in terms of your agents, remember agents help other chemicals get oxidized, get reduced. They themselves do the opposite. So for example, I just labeled NaOCl actually got reduced. Which chemical allowed it to actually pick up the electrons? Which chemical gave it its electrons? It was only because this AS4 was in compound. So therefore, AS4, not only can we say it's the chemical that was oxidized, this one here is actually the reducing agent. It allowed the NaOCl to reduce. The NaOCl here, which was actually reduced, we can refer to this one here as the oxidizing agent. As you're defining agents here, don't say, oh, it's the thing that gets reduced. That's just by consequence. Just state that, oh, it helps someone else reduce or it helps someone else oxidize. Okay. So hopefully that clarifies some terms from the previous lesson. Over the next 2 classes here, we're going to focus on balancing redox reaction. In terms of balancing, they're just going to give you, obviously, an unbalanced equation, no coefficients yet. when they say balance a reaction, they actually want you to balance. So balancing redox reaction. Well, why are we learning balancing? I know how to balance stuff here. The thing that we're adding, because redox reactions actually involve an electron transfer, when we balance redox, we actually need to balance for number of atoms. That's what we usually do. Let's make sure conservation of mass, make sure all the atoms are accounted for. But we also want to make sure, as electrons are passed from one place to the other, that the electrons themselves are also all accounted for. So balance for number of atoms and total charge, which makes sure that all the electrons, sure, they can be passed from one chemical to another chemical, but all the electrons are always present. We're going to learn two different methods to do this balancing. Today I'm going to teach you the half reaction method. They're not going to force you to do one method over the other method. They're just going to say balance. Whichever method you're more comfortable, you can do it that way. Half reaction method here, as you walk away through, for balancing redox equation, it's actually really, really systematic. Okay, here's our strategy. Part A, what we're going to do, I want you to break up the equation that we have, separate your redox reaction into two half reactions. Since a redox reaction is part reduction and part oxidation, I want you to break up which part is oxidation, which part is reduction. What we're going to do is we're going to balance each half, balance the half reactions. We're going to be using a mnemonic here, major hydroxide. Okay, this is actually giving you the order here. We're going to balance major atoms first, then oxygens, then hydrogens, then the charge. More on this later. And then finally, once your half equations are balanced, we're going to combine them back together. Combine, so electrons cancel. Okay, and I'll walk you through this step by step so that we know what we're talking about here. But that is one method to actually do balancing. So let's just try out a question. Again, on the workbook questions, they're just going to ask you balance. They're not going to say balance using half reaction method or the other method tomorrow's oxidation number method. They just want you to balance. So let's say I go from the U plus 4, MnO4 minus, Mn plus 2, and becoming UO2 plus 2. Right? They could just be asking you this as a multiple choice question. Who gets oxidized, who gets reduced? We're going to find that balancing is actually fairly tedious. Unless they really are looking for the coefficients, I can just more easily, I can just go, well, uranium here is going from a plus 4, the oxidation state over here is sort of like a plus 6, going from 4 to 6 is an oxidation. I can identify who is oxidized and reduced, just like we practiced earlier. I only do this balancing here if they actually want to know what coefficients make sure all the atoms are accounted for and all the charges are accounted for. So, first step, separate our redox reaction into two parts. How do I know that there's two half reactions and how do I separate them? Usually the elements have to be conserved. So if I have a uranium in a compound, it'll probably become another compound with uranium inside of it. So as I break that up, uranium plus 4 becoming the other uranium compound UO2 plus 2, I just copy it out exactly. How about this permanganate here? The permanganate reacts to produce manganese plus 2 here. That's probably a half reaction. The manganese probably goes to the other thing that has manganese. That's the first step. I've broken up the two half equations. I'm assuming if this is redox, one of these is going to involve in loss of electrons, oxidized. One of these is actually going to have gained electrons. Okay. How do we do this balancing here? I'll give you a few sort of middle steps here. We again use this acronym, major hydroxide. Okay. Sort of in order left to right here. We balance our major atoms by inspection. What I refer to as major atoms, this is everything except for O and except for H, because those ones I'm going to balance later on. Okay. So what's a major atom here? Uranium is a major atom. That's not O or H. I'm going to balance for the number of atoms. I have one uranium, one manganese, one manganese. Perfect. Okay. Now I know, wait, the uranium here is actually a plus 4 and the other one isn't compounded. I'm just looking at the number of atoms at the moment. Okay, so I balance that, check. Next I'm going to balance here is I'm going to balance the oxygens, right? For the oxygens, I'm going to balance the oxygens by adding waters. Turns out a lot of these redox equations, because they involve chemicals that are charged, usually a lot of these actually take place in aqueous solution. Because we are actually in solution, we're going to have water present. Water will actually help me make sure the oxygens are accounted for. So now we actually deal with the compound problem here. We have 2 oxygens on the right side. Don't worry about the charge. 2 oxygens. I don't have any oxygens here. I'm going to add 2 waters to the left-hand side. So this is what I like doing here. After I break out the half equations, I try to put this in the middle, and then that way as I'm going through balancing the half reaction, I add things to the left, add things to the right, just to make sure everything is accounted for. Why was it 2 waters? Well, every water comes with 1 oxygen. 2 times oxygen here gives you the 2 oxygens here. Here, the permanganate actually has 4 oxygens. I don't have any oxygens so far. I would need to add 4 waters to this side here. Again, I haven't worried about the charges yet. The charges get balanced as a really, really last step. Okay? At the very least now, the number of atoms of oxygen should now be matched up. 2 O's, 2 O's, 4 O's, 4 O's, perfect. But now, when I actually added waters, I've actually screwed up the H's. H's are going to come next. To balance the H's, we're going to balance H by adding H+. Okay. Most of these solutions here not only are going to be aqueous, there's a lot of water present, most of them are actually going to be acidic in nature. If they didn't specify which one it is, you can assume it's acidic. Obviously, if they put a bracket acidic, you can do it this way as well. Later on, after we get some practice, I'll show you what it would look like in basic if we don't have an excess of H+. So again, we're just balancing for number of atoms so far. At first, I didn't have any H's. But now that I've actually added waters, I now have 4 H's on the left side. I don't have any H's on the right side. I'm going to add plus 4H+ on the right-hand side. Okay? Now, at least the number of atoms are matched up. Let's do the same on the bottom. We had no H's on the left. On the right-hand side, I have 4 times 2. I have 8 H's. So what I'm going to do is I'm going to add 8 H+ to the left-hand side. Right? It's not always going to be, oh, you added water to one side, you have to add H+ on the other side. You just want to look at what the half equation is. At this point, you can do a check for yourself. All the number of atoms should be accounted for. Okay? This is actually finally the step here. Now we want to worry about the charges all at once. We're going to balance off the total charge. Okay? We're going to balance by adding free electrons. Now, I've been telling you here, charges are unstable. Our total redox equation should have canceled out all the electrons. That was the last step we're going to do later on. But since these are half equations, since this is just showing you the different parts of the entire equation, we can add electrons no problem. Okay? So how do we do this here? This time we look at the total charge. So careful of the coefficients here. Uranium here has +4. Water has no charge. 2 times no charge is just 0. The total charge on the left is sort of like a +4. How about the total charge on the right? The UO2 compound here has a +2. Every H has a +1, but there's 4 of them. In total, this one here has a +6. Okay? Earlier we were dealing with sort of, well, what's the oxidation state and whatever. This time we're doing as a whole. So I have a +4 in total on my reactant side, a +6 in total on my product side. I'm going to add electrons. The electrons are going to bring my charge down. I want to make sure that these numbers match. They don't have to equal 0. They just have to match each other. So I have one side that's +4, the other side is +6. What I'm going to do is I'm going to add 2 electrons to the right-hand side. By adding those 2 electrons, +6 minus those 2 electrons gives you a total charge of +4. +4 and +4 end up canceling out perfect. And it is actually at that point, oh look, electrons are actually on the right-hand side. When they're on the right-hand side, that means something has lost electrons. The reactant that was involved, the U +4, has actually been oxidized. That refers to a loss of electrons. This is actually the oxidation half equation. I had broken up the 2 halves, but I didn't know whether it was oxidized until this last step here. Because that one there is an oxidation, I would expect the other half equation to be the reduction. This is to be the gaining of electrons. It's the reactants that were involved that actually gained. So MnO4- is the chemical that actually gets reduced. I just want to know by how many. Let's deal with the total charge again. So what's the total charge on the left? +8 minus the 1 gives you a total charge of +7. On the right-hand side, I have +2. Water is neutral. I have a +2. I always add to the side that has a higher charge and add electrons until it comes downwards. So we're going to add those electrons here. I want to add 5 electrons to the left-hand side. By adding those 5 electrons, 7 minus 5 ends up giving you plus 2 on both sides. Now everything is matched up, and we have electrons on the left-hand side, so it's a reduction. The MnO4 has picked up those electrons. When they become Mn2+, they sort of have the electrons inside of it. Okay, so that was actually a lot of work. We took a redox equation. We broke up the 2 halves. For the 2 halves to balance each part, we went through balance the major atoms, whatever's not O or H. You balance the oxygens by adding waters. You balance the hydrogens by adding H+, and then finally you balance the charge by adding electrons. Each half equation is now balanced, so we're now well on our way. There is one last step now. Because our whole equation was actually just one full redox equation, I need to put these 2 equations together. So we're on we just balanced the half equations, we followed this sort of acronym here, then we want to combine it together so that the electrons end up canceling out. We don't want to have any free electrons in nature. Free electrons are fine for the half equation, but when I get back to my overall expression, this one here can't have free electrons. Here's the problem. Every time I run this first reaction once, it's only going to drop off 2 electrons. Every time I run the reduction reaction, it wants to actually pick up 5 electrons. What I want to do is I don't want to have an excess. If I just did 1 of each, I would have a net of 3 electrons. This equation wouldn't even run because the oxidation only has lost 2 electrons. What you're going to do as a final step, you're going to take these 2 equations and you're going to find the lowest common multiple. So find the lowest common multiple, the LCM, the lowest common multiple in this question between 2 and 5. Right. What do both 2 and 5 go into? Well, both of them actually multiply into 10. Right? How many times would you need to run the oxidation reaction so you get 10 electrons? Every time you run it, it's 2 electrons. Let's multiply the first equation by 5. Everything involved is going to now be scaled up by 5. How many times do you need to run the second reaction here to get 10? You're going to, again, multiply it by 2. And here, finally, we're done. We're going to take these expressions here. We're going to do the multiplications. What you want to imply is all of these guys here on the left, all of them go as reactants. All of these on the right go as products here. I'm going to go through. You can double check my numbers. I'm going to multiply the first equation by 5. So 5 times 2 gives you 10 waters. 5 times U plus 4 is 5 U plus 4. These ones here are reactions in the reduction reaction. Those get multiplied by 2. I'm not going to bother going 2 times 5, 10 electrons. I had set it up so those electrons cancel, so those are gone. 2 times 8 gives you 16 H+. 2 times MnO4 gives you 2 permanganate. This one here ends up giving you 5 UO2 plus 2. 5 times 4 gives you 20 H pluses. 2 times Mn2 plus gives you 2 Mn plus 2. And then 4 times 2 ends up giving you 8 waters. So I know it's a really scary expression, a lot of waters and H pluses have popped up, but seeing as we balance both half equations, we balance both bits, this one here should now be balanced. Because I had balanced these equations separately, I had H pluses and waters, you might find, like we do in this situation, I actually have 16 H pluses here, and I have 20. There's no point in having H plus on both sides. Even though the numbers don't match up completely, I can get rid of these 16, leave me 4 H pluses there. Similarly with waters, I have 10 waters, I have 8 waters on this side. What if I got rid of these 8 waters, completely gone, subtract this one here by 8, ending up giving you 2 waters. Let me clean this up here. So 2 waters and 5U plus 4. Make sure you scale out the equations properly. Make sure you write down all the charges exactly, or else the expression won't be balanced. So when I clean this up here, that seemingly is what I have. Let's check to make sure that this is now balanced. Is it balanced in terms of atoms? Is it conserved in terms of how many of each element? 2 times 2, 4 hydrogens, 4 hydrogens. 2 times 1, so I have 2 oxygens, plus 2 times 4, 8 oxygens there. I have 10 oxygens total. 5 times 2 is 10 oxygens, good. 5 uraniums, 5 uraniums. 2 manganese, 2 manganese. Yep, atoms are balanced for. Typically that would be done. I'm balanced, mass is conserved. But for these redox reactions, I also want to check that the total charge is accounted for. This makes sure that there's all the electrons have been picked up. We had made sure that when we put it back together, we can check the total charge one more time. The total charge here, every uranium has plus 4. There's 5 of them. That gives you plus 20. Minus the 2 from the permanganate gives you a total of plus 18 on the left side. On the right-hand side, I have 5 times 2 plus 10, plus the 4 here, plus the 4 here. Great. Plus 18, even charge is balanced for. This is a fully balanced redox reaction. All the electrons are accounted for. Okay. So lots of work, but very, very systematic. Break up the two parts. Let's balance off the two parts separately, and then let's put it back together. Usually I find it's taking so much time already. I don't have time to check the atoms. Usually I just check the total charge. There's so many ways that the charge could have been different. If by the time the charge is actually matched up, we're probably all fully balanced. Okay. So let me just practice through one more of these with you here. There's one last little spin-off at the end. I want you to just balance. Again, they're not going to force you. Maybe in the workbook they just say for practice, balance using half reaction method. But finally on the exam, they're just going to say balance. I'm going to give you this expression here. We have zinc. We have an arsenic compound, As2O3. This becomes AsH3, and this becomes Zn plus 2. If this were a multiple choice question just asking you who's oxidized, who's reduced, just do it using oxidation numbers. I only do this balancing work here, super tedious if they ask me to balance. The little twist in this question here is I'm going to ask you to balance the solution here actually in basic. Okay. Fortunately for us, the first part of it, I want you to just pretend it's acidic. So balance as an acidic solution, just like we did before, right? Well, what did we do before? We broke up the half equations, so break into half equations. We balanced the half equations by following that major hydroxide acronym, and then we combined by canceling them. So we're going to do all that again. If they emphasize that it is basic, I'm just going to add one last step at the really end. Okay, so let's just do some practice here. How do I separate this into half equations? Probably the zinc is going to become the other zinc. So one equation is going to be Zn becomes Zn plus 2. The other one is going to be the arsenic compound. Write it down completely. As2O3 becomes AsH3. That's weird, right? What happened to the O's and H's? Well, we're actually going through the half equations to actually balance them. Let's follow through our method. Do not forget to balance the major atoms. A lot of people start getting comfortable. Oh, yeah, add water for O, add H plus for H's. That's good, but you have to make sure that the major atoms are balanced first. So major atoms are everything that's not O or H. I have one zinc. Good. I have 2 arsenics. Oh, no, I only have 1 arsenic. That already means I need to put a 2 here. You see, if you forgot that 2, you might be able to balance the O's and H's and then end up realizing later on, oh, no, the arsenics actually don't balance. So always make sure the major atoms are balanced first. I would encourage you just to pause the video, try it out for yourself, see if you can balance the oxygens by adding water, see if you can balance the hydrogens by adding H+, and then as you add the electrons, you can identify who's oxidized and who's reduced. Let's try it out here. So first equation, major atoms are good. There's actually no O's, so we're fine there. Second equation here, we have 3 O's. I don't have any O's, even with that 2 there. So I'm going to add to the side that I don't have oxygens. Every water only comes with 1 oxygen. I need to add 3 waters to the right side. That gives you 3 oxygens, 3 oxygens. Perfect. How about in terms of H's then? First equation again is easy. There's no H's, balanced. How about the second equation here? I have absolutely no H's. I actually had 2 times 3. I already had 6 H's. And now by adding the 3 waters, I've added another 6 H's. Now I have 12 H's altogether. How many H pluses do I add to the left side so that at least the number of H's match up? Hopefully you're able to say to me here, plus 12H plus, right? It's an acidic solution here. We'll deal with this basic part towards the end. And finally, we can deal with this total charge bit. The total charge on the left side, elemental, this is 0. This one here is an ion is plus 2. You always add to the side that has a higher charge, and it's going to bring the charge down. So you have a plus 2 there. I want to add 2 electrons, and therefore we have 0 charge matching up 0 charge. How about the second equation? The total charge on the left side, every H has a plus. There's 12 of them. That gives you a plus 12. On the right-hand side here, we have neutral. So plus 12 and 0. What I want to do is I want to add 12 electrons. At that point there, if the electrons on the left side, we know this equation is oxidation. If the equation has electrons on the left-hand side, this one here, we know it's a reduction. Okay, so electrons have been passed from the Zn over to the As2O3. Okay. At this point here, your half equations are now balanced. Okay. What I'm going to do is I'm going to the lowest common multiple, match up the electrons that have been transferred, and make sure that there's no free electrons. When I get this equation all together, I want to make sure there's no free floating electrons, charges in general are unstable. What's the lowest common multiple between 2 and 12? Although you could say 24, in fact, they both go into 12. So if this second reaction here always needs 12 electrons to be gained, I just need to run this first reaction 6 times. I'm going to run the second equation just once. At that point, we're ready just to put everything on the left, everything on the right, and the electrons are set to cancel. So double check my numbers here. So I have 6 zinc. I'm not going to bother showing the 12 electrons because I had done lowest common multiple to ensure that the electrons are all accounted for. 6 zinc plus the 12H plus and the arsenic compound. This one here wasn't scaled up or anything like that, so just write it down. The first equation also has 6Zn plus 2. And then I'm just going to copy down the 2 ASH3 and the 3 waters. Okay. At that point there, we should be balanced. Okay. This time we don't have H pluses on both sides, water on both sides. This one here should be good. Again, if you're running out of time, I would just check the charges. In total, I have every H is plus. There's 12 of them, plus 12. 6 times 2 is also plus 12. Probably we're good. And now we're going to address this last little spin-off. We've so far balanced in acidic, because this one here happens to have an excess of H+. In fact, as we get to our table, the table will also have all the half equations all balanced. Anytime you see H+, it tells you you need to have protons in solution. If you don't have protons, the equation can't run. Just like we can't run this reduction reaction without As2O3, we can't run the reaction without the H+. So if they ask you to balance this equation, but in basic, you're going to have balance in acidic just like we did. That's some good practice from earlier. And all we're going to do is we're going to add one last step. There's 2 ways of doing this. To change it to basic, put this down here. To change to basic, add enough OH minuses to cancel the H+. Simple as that. So I'm going to take this equation. That one there should already be balanced. I have 12 H pluses. I'm going to imagine add 12 OH minus on the left side. Algebra says whatever I do to the left side, I have to do the right side to keep things balanced. Yes, we learned in our acid-base chapter, somehow the H plus acidic cancels out the OH minus, but it's not like they disappear though. H plus combining with OH minus actually ends up forming 12 waters. And now we actually do have waters on both sides here. You can then say, well, I had 3 before. Let's get rid of those 3 and let's make this a 9. Let me clean this up. So I'm going to have 6Zn plus 9 waters. In the presence of As2O3 ends up giving you 6Zn plus 2, the 2 ASH3, and don't forget the 12 hydroxide that we added. Now I have the expression expressed in terms of hydroxide instead of H+. Now this equation doesn't need acidic conditions to happen. Okay? So if the equation here, if it doesn't specify acidic or basic, assume it's acidic. If it says bracket acidic, we're done. If it says bracket basic, do everything in acidic, just like we did here, and then just one last step here for basic, add enough hydroxides to both sides to end up canceling out. Just let me show you for completeness sake here, how else could you have done this conversion to basic? What you can do is you can actually add the self-ionization of water. So let me just recopy this down here, or 6Zn and 12H plus, As2O3, becomes 6Zn plus 2. This was it balanced in acidic solution. Earlier we had 3 waters. Okay. To convert to basic, again, the goal is to get rid of these H pluses. What I did is I added hydroxide to directly neutralize it. What you can do is you can add self-ionization water. If I have 12 H pluses on the left side, I'm going to actually add 12 H pluses. The self-ionization water has the H plus and hydroxide in 1-to-1 ratio. So I have 12 waters. Imagine adding this equation in. Therefore, 12 H plus on the left cancels 12 H plus on the right. That also ends up giving you the 12 waters. 3 of them will cancel out there, so that gives you 9. It gives you the 12 hydroxide. It will give you the same expression. So you could think of this as add the self-ionization of water to end up canceling out the H plus. Okay. So all this, it just takes practice. I know it's really, really systematic. Make sure you don't drop any charges along the way. Tomorrow we'll come back, we'll practice this half reaction method, and I'll teach you one other method to do balancing. Right? Thanks, guys.